The burning moon that shouldn't exist. When scientists at NASA first turned their instruments toward Jupiter's innermost large moon, they expected to see another frozen, cratered world like so many others in the outer solar system. Instead, what they found shattered assumptions and rewrote planetary science forever. The moon was named Io, and nothing about it behaved the way it should. Orbiting the giant planet Jupiter at terrifying speed, Io exists in a gravitational war zone. It is stretched, squeezed, and twisted by Jupiter's immense gravity and by the tug of neighboring moons, turning it into the most volcanically active world ever discovered. This was not speculation. It was not theory. It was directly observed. The turning point came in 1979 when the spacecraft Voyager 1 flew past Jupiter. What its cameras captured stunned mission scientists. Instead of a quiet, frozen surface, Io displayed towering plumes erupting hundreds of kilometers into space. Active volcanoes were caught in the act. Lava fountains burst across a moon half the size of Earth's. It was the first time humanity had seen active volcanism beyond our planet. In that single moment, Io went from being a minor speck in astronomical catalogs to one of the most extraordinary objects in the solar system. Before that discovery, most scientists assumed moons that far from the sun would be geologically dead, frozen solid relics of ancient formation. Solar heating at Jupiter's distance is weak, and Io is far too small to retain the kind of internal heat that powers Earth's volcanoes. Yet there it was, brighter, hotter, and more violent than any volcanic landscape on Earth. The question was unavoidable. What was powering this inferno? The answer was both elegant and terrifying. Io is trapped in what is known as orbital resonance with two of Jupiter's other major moons, Europa and Ganymede. This gravitational interaction prevents Io's orbit from becoming perfectly circular. Instead, its orbit remains slightly elliptical. As Io moves closer to and farther from Jupiter, the planet's gravity flexes the moon like a stress ball. This constant flexing generates enormous friction inside Io's interior, a process known as tidal heating. The result is internal temperatures so extreme that rock melts on a planetary scale. Imagine a world where the ground beneath you is never truly stable, where mountains collapse under the force of internal magma surges, where lava lakes glow brighter than city skylines at night. That is Io. Surface temperatures near volcanic vents can exceed 1,600 degrees Celsius, hotter than most eruptions on Earth. Sulfur and sulfur dioxide coat the surface in brilliant yellows, reds, oranges, and whites, giving Io an almost alien, painted appearance. The colors are not artistic illusions. They are chemical scars from constant eruptions. When Voyager 2 followed its twin spacecraft later in 1979, it confirmed that the volcanic activity was not a rare event captured by coincidence. It was continuous. Io was in a perpetual state of eruption. Massive plumes rose and fell. Lava flows reshaped the surface in real time. Impact craters, so common on other moons, were almost entirely absent. They had been buried or erased by fresh volcanic material. Io's surface is one of the youngest in the solar system, constantly renewed by fire. Years later, the spacecraft Galileo arrived at Jupiter in the 1990s, providing even more detailed observations. Galileo detected enormous lava lakes, some larger than entire metropolitan regions on Earth. One of them, Loki Patera, became famous for its periodic brightening events, evidence that its crust repeatedly sinks and resurfaces in waves of molten rock. These observations were not just visually stunning, they provided critical data about how tidal heating works deep within planetary bodies. NASA's findings on Io forced scientists to rethink how energy operates in space. Until Io, internal heat was primarily attributed to radioactive decay or leftover heat from planetary formation. Io demonstrated that gravitational interactions alone can generate extraordinary thermal power. This revelation expanded the search for potentially active worlds far beyond traditional assumptions. If tidal forces could melt rock on Io, what might they do beneath the icy crust of Europa? Could similar forces heat distant exoplanets orbiting massive stars? Io became more than a curiosity, it became a laboratory for cosmic physics. But Io's violence is not confined to its surface. The moon also interacts electrically with Jupiter. As Io moves through Jupiter's powerful magnetic field, it generates a massive electric current, millions of amperes flowing along magnetic field lines between Io and Jupiter's poles. This current creates intense auroras in Jupiter's atmosphere and contributes material to Jupiter's magnetosphere. Io is not just orbiting Jupiter, it is feeding it, electrically and chemically. Volcanic gases escape Io's weak gravity and form a torus, a donut-shaped ring of charged particles, around the planet. This constant exchange of matter and energy makes Io part of a dynamic system rather than an isolated world. NASA's instruments detected sulfur and oxygen ions streaming through space, evidence that Io's eruptions extend far beyond its surface. Entire regions of space around Jupiter are influenced by Io's volcanic output. The Moon is effectively reshaping its planetary environment. And yet, despite its chaos, Io follows precise physical laws. Its eruptions are driven by measurable tidal stresses. Its orbital resonance is predictable. Its lava composition can be analyzed spectroscopically. The violence is not random, it is the result of gravitational mathematics playing out on a colossal scale. That duality, chaos governed by order, is what makes Io so scientifically powerful. NASA's continued observations, including those from the Juno mission, have added new layers to the story. Juno's instruments have detected hotspots, mapped heat flow, and captured new images of volcanic regions. Even decades after Voyager's discovery, Io remains active. It has not calmed down. It has not stabilized. It is still erupting. What makes Io truly extraordinary is not simply that it has volcanoes, it is how those volcanoes are powered. On Earth, volcanism is driven by heat trapped from formation and radioactive decay in the mantle. On Io, radioactive decay plays only a minor role. Instead, tidal heating dominates, turning orbital mechanics into a planetary furnace. Every time Io completes its orbit around Jupiter, roughly every 42 hours, it is stretched and compressed by as much as 100 meters in vertical displacement. The entire Moon physically flexes. Imagine continents rising and falling by the height of skyscrapers twice every 2 days. This constant motion grinds rock internally, producing heat on a global scale. NASA scientists used data from Galileo to model Io's interior. They found evidence suggesting a partially molten mantle beneath a relatively thin crust. Some regions may even contain subsurface magma oceans. Unlike Earth, where magma chambers are localized, Io's interior could contain vast interconnected reservoirs of molten rock. This explains the sheer number of eruption sites. Over 400 active volcanoes have been identified. One of the most dramatic volcanic features observed was the plume of Pele, rising nearly 300 kilometers above the surface. For comparison, commercial airplanes fly at about 10 kilometers altitude. Pele's plume was not just high, it was sustained. The material erupted at such velocity that it escaped Io's gravity and contributed to the surrounding plasma torus. NASA's instruments also revealed that Io's lava composition might be ultramafic, extremely rich in magnesium, suggesting eruption temperatures hotter than most modern Earth volcanoes. Some researchers propose that Io's eruptions resemble those of early Earth billions of years ago, when our planet was far more geologically violent. In that sense, Io offers a window into Earth's distant past. The surface is constantly reshaped. Lava flows can stretch hundreds of kilometers. Sulfur dioxide frost condenses in colder regions, creating bright white deposits that contrast sharply with dark lava plains. Entire landscapes transform within months. When Galileo revisited certain regions, they had already changed dramatically from previous images. NASA also discovered towering mountains on Io, some taller than Mount Everest. These are not volcanic mountains but tectonic features formed by compressional forces within the crust. The same tidal stresses that melt the interior also fracture and uplift the surface. Io is not just volcanically active, it is tectonically restless. And then there is radiation. Io orbits within Jupiter's intense radiation belts. Any spacecraft passing nearby must endure extreme particle bombardment. This environment complicates exploration and threatens onboard electronics. Yet despite these hazards, NASA missions have continued to gather invaluable data. What NASA found on Io was not a static object, but an ongoing process, a demonstration that celestial bodies can remain dynamic long after formation. Gravity, resonance, magnetism, chemistry, and geology all intersect here. Io is a symphony of physical forces playing at maximum volume. Why Io changed everything? The discovery of Io's extreme activity did more than add a fascinating chapter to planetary science. It reshaped the search for life and habitable environments. If tidal heating can melt rock on Io, it can also melt ice elsewhere. Beneath the frozen crust of Europa, tidal heating may sustain a subsurface ocean. Similar processes might operate on Saturn's moon Enceladus. Io proved that distance from the Sun does not necessarily mean geological death. NASA's findings expanded the concept of the habitable zone. Instead of focusing solely on stellar warmth, scientists now consider internal heating mechanisms. Worlds once dismissed as too cold may harbor internal oceans or geothermal activity. Io's violence indirectly strengthened the case for exploring other icy moons. Future missions may study Io in greater detail, potentially deploying advanced instruments capable of mapping its interior more precisely. Understanding Io helps scientists refine models of exoplanets subjected to intense tidal forces around massive stars. Some exoplanets may experience tidal heating even more extreme than Io's, turning them into lava worlds on a colossal scale. Io stands as proof that the universe is more dynamic and unpredictable than once believed. NASA expected ice and craters. Instead, they found fire and transformation. They found a moon that defied assumptions and demonstrated the raw power of gravity. In the end, what NASA found on Io was not just volcanoes. They found a mechanism capable of reshaping worlds. They found evidence that planetary systems are interconnected, that moons can influence planets, and that energy can come from motion itself. Io continues to erupt. It continues to glow in infrared images. It continues to challenge our understanding. And as long as spacecraft keep watching, it will continue to reveal new secrets, each eruption a reminder that even in the cold darkness of the outer solar system, there are places where the ground itself burns.